Hello, friends. We are continuing our study of geometry, and this time we're going to be doing another one of these logic lessons, which again doesn't feel like mathematics, but it is. In fact, what we're going to do this time, our last logic lesson was inductive reasoning, finding patterns, basically, the idea of conjectures, disproving conjectures with counterexamples, etc. This one, though, we're going to be beginning what we call deductive logic. And we're going to start with just this idea of what a conditional statement is. Let's begin. A conditional statement is basically an if-then statement, right? We abbreviate it if P then Q, where P is like some statement of some kind, right? Some proposition, and then Q is some other proposition. So, for example, if today is Friday, then tomorrow is Saturday. Today is Friday is represented by P, and then tomorrow is Saturday. That's a separate proposition, is Q. We, in symbolic form, we write this P arrow Q. Think of it as like P implies Q. If P, then Q. So if P, then Q. Another example would be if an animal is a mammal, and I wrote that twice. So if an animal is a mammal, we just want to make sure it gets into your head. Then it is a dog. Okay. Now think about that for a minute. Don't think about my typo, or I wasn't typing, so I guess my righto. If an animal is a mammal, then it is a dog. Uh, is that true? No, it's not, right? Because we know that if it's a mammal, so that's kind of like what we say the promise. And then does it deliver on the promise that if it's a mammal, then that means, it implies that it is a dog? No. Now, this is still a conditional statement. It still is in the form if P then Q. You can fill in anything you want with any types of propositions in there, if P and Q. It doesn't matter if they're true or false. It's still a conditional statement. The truth value of the whole conditional statement, now that does depend on whether or not those things are true or false. And we're going to look at that in just a minute. So this is an example. If an animal is a mammal, then it is a dog. Another example, if the sun is in the sky during the night, then all men are mortal. Again, what? So the first proposition, the sun is in the sky during the night. That's not true, because the sun is not in the sky during the night. And then the conclusion, all men are mortal. Well, that is true. So how does that work? What's the truth value of that statement if the what we call the hypothesis is false, but the conclusion is true? And so that's what we call this, by the way. The beginning part, the P is called the hypothesis, and the Q is called the conclusion. And P can be true or false, and Q can be true or false. So when do we consider in symbolic logic, deductive logic, and again, you're probably thinking to yourself, this is geometry, this is math. What are we doing with this? But really, again, what we're doing here is we're laying the foundation of logical thinking that we're going to use in geometry, and really that you use, uh, hopefully, all the time. Right? This is the foundation of every subject. It's just rarely ever, um, elucidated in this way and explained. Okay, so things you need to know, right? A conditional statement, if P then Q. P is the hypothesis, Q is the conclusion. The truth table for this looks like this. Okay, so if you have a statement where both the hypothesis and the conclusion are true, then the whole conditional itself is considered true. If you have a conditional statement where the hypothesis is true but the conclusion is false, then the whole conditional statement is considered false. You can think of it this way, that the hypothesis makes a promise, and then the conclusion delivers on that promise. And so if the hypothesis is true and the conclusion is false, it doesn't deliver on the promise. However, if we have, and this is a little bit confusing, it's counterintuitive at first. If you have a conditional statement where the hypothesis is false, then the whole statement is considered true. It doesn't matter if the conclusion is true or false. Well, how does that work? You can think of it this way: it's like the promise was never made, and so this would be um, uh, this would be an example like this one, right? If the sun is in the sky during the night, so this one, that's false. So there's no promise that's ever made, because the way we started off, it doesn't make any sense. Then all men are mortal. So it doesn't matter if this conclusion is true or false, because uh, the hypothesis was false. So there's no promise made. So there doesn't need to be any delivery on the problem, on the promise. So this is the the truth table. We call this the truth table because this exhausts the possibilities, right? Notice how we lay this out. So P, true, true, false, false. And Q is true, false, true, false. These are the only combinations you can have. And order matters in these combinations, by the way. Right? So true, 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 false, false, true, false, false. We set it up like this. This is a pattern that you're going to see because we want to set it up in an orderly way that exhausts all the possibilities instead of just trying to think, well, this can be true and that can be true and this could be true, that could be false. So wait, did I do that yet? We do it in an organized way. Very common. You're going to see truth tables. It's basic to the study of logic and deductive reasoning. Okay. Another idea here is that we can switch. Right? If the original statement is in the form if P then Q, the converse of the conditional is if Q then P, where we switch the propositions. Okay, we switch the hypothesis and the conclusion. Here's how I remember this, and I still think this when I have to deal with this: that a con artist tries to switch his identity. Right? There are going to be some other things like inverse and contrapositive. We don't have to go into that now, but just so you know, there are others. So you're going to want to remember that a converse is when we switch the hypothesis and the conclusion. So, for example, if today is Friday, then tomorrow is Saturday. This is a conditional statement. The converse of that is that if tomorrow is Saturday, then today is Friday. And notice both of these are true. Or actually, right now it happens to be Monday, right? But if it were Friday, then this would be true and this would be true. And then if you can think of it this way, right? If tomorrow is Saturday, then today is Friday. They both imply each other, right? Today being Friday implies that tomorrow is Saturday, and tomorrow being Saturday implies that today is Friday. So here's a case where you have a converse where it's true in both cases. The original conditional and the converse are both true. So here are some examples. I want you to evaluate the truth of the statement and its converse. Right. So if an animal is a snake, then it is a reptile. Well, this one would be true, right? If an animal is a snake, okay, and so we're picking a random, but if there's an animal that happens to be a snake, then that does imply that it is a reptile. Okay, and then what's the converse? The converse is, let me write this thinner so I can fit it. Right, the converse is if an animal is a reptile, then it is a snake. That's the converse, and it's false because being a reptile does not necessarily imply that it's a snake. So sometimes the converse will be false when the original conditional is true. Okay, so if I am a reptile, then you are a fish. No offense intended. I mean, I'm calling myself a reptile. But anyway, it's all just for the sake of learning here. So in this case, both statements are false. If I'm a reptile, then you're a fish. I'm not a reptile. You're not a fish. Um, Neither reptiles nor fish have rational abilities. In order for you to be doing anything with this video, even to have access in the first place, you need rational abilities. And so you are not a fish because that rules out, right? And so I just included a bunch of conditional statements, right? So if you have rational abilities, you're not a fish. You have rational abilities, therefore you're not a fish. That's so they were putting it all together, but we're getting ahead of ourselves. Anyway, the conditional as a whole, though, is considered true because both statements are false. If the hypothesis is false, the whole statement is considered true. Again, counterintuitive, but again, there's no promise to deliver on. The converse is this: if you are a fish, then I am a reptile. In this case, again, the converse is true because you're not a fish. So the hypothesis is false, and in our truth statement, our truth table, that would be down here. We're in this last line. Both of those are false, and so the whole conditional is considered to be true. And our last example: if you give a mouse a cookie, he will ask for a glass of milk. Um, this line has been embedded into my mind. I have a 3-year-old and a 5-year-old at home, and I read this story every night. I could probably recite the entire thing for you, but regardless, if you give a mouse a cookie, he will ask you for a glass of milk. It's a conditional statement, And so we can evaluate it. So you give a mouse a cookie. Uh, so that it might be true or false. We don't know. But let's just say that you did give the mouse the cookie according to the rules of the book, which is gospel truth. Then he will ask for a glass of milk. So this is true, right? um, if, however, like if it's me, I'm not giving the mouse a cookie, so that would be false. Either way, um, the converse, it says, would be this: if a mouse asks for a glass of milk, you will give him a cookie. The conditional, the hypothesis, right, the beginning part, that is false. A mouse cannot ask for a glass of milk. And so um, the overall truth value of the statement is true because the hypothesis is false. So there you go. Introduction to another logic. Very beginning of deductive reasoning. Not that we did any deductive reasoning, but learning about conditional statements is a first step towards doing that. Thanks for watching. If you watch, then you will subscribe.